Hi everyone! Today, I'm going to talk about SRv6, which is short for Segment Routing over IPv6. SRv6 simplifies existing IP network protocols and supports network programmability. And because SRv6 is compatible with IPv6 devices on existing networks, SRv6 capable devices can be deployed together with IPv6 devices to maximize the return on investment. SRv6 plays an important role in building automated, simplified, and intelligent IP networks. Although there are a lot of SRv6 related materials available already, SRv6 is actually a new protocol. Against this backdrop, many people have the following questions. How is SRv6 configured? And what protocol extensions have been implemented for SRv6? Let's dive into the details to answer these questions. Our course focuses on the EVPN L3 VPN v4 over SRv6 BE scenario. SRv6 supports two forwarding modes, SRv6 BE and SRv6 TE policy. BE stands for best effort. Comparatively speaking, BE does not have the traffic engineering capability. As for the SRv6 TE policy mode, we will discuss it in later courses. In EVPN L3 VPN v4 over SRv6 BE, EVPN is a control plane concept in comparison with conventional BGP L3 VPN v4. Even though it appears to be a service type. An L3 VPN v4 indicates that IPv4 is deployed between a PE and a CE, and the CE carries IPv4 services. Let's take a network with 5 devices as an example to describe how EVPN L3 VPN v4 over SRv6 BE is configured. We'll also introduce the application scenarios of key commands involved here. In addition, to help you understand the configurations, we'll look at the associated packet formats based on packet headers obtained on the specified interface of PE1. After that, I will show you how to verify the configuration and make a brief summary. First, let's look at the network example. PE1, the P, and PE2 on the network belong to AS100. And can be regarded as a carrier's public network devices. CE1 and CE2 are customer-aid devices. It's required that a bidirectional SRv6 BE path be established between PE1 and PE2 to carry IPv4 services between CE1 and CE2. To meet this requirement, we can break down the configuration procedure into 3 main steps. The first step is to configure is on PE1, the P, and PE2 to achieve root reachability. The second step is to configure SRv6 on PE1 and PE2. And the third step is to configure CE access on the PEs and establish a BGP EVPN peer relationship between them, so that routing information of the CEs can be transmitted between them. Let's start by looking at how to configure is. Is configuration consists of both global configuration and interface-specific configuration. We'll talk about global configuration first. It involves several key commands, the first of which is isLevel. Is supports both Level 1 and Level 2. Level 1 is mainly used in an edge area and is responsible for intra-area routing, while Level 2 is used in a backbone area and is responsible for inter-area routing. A Level 2 device can connect different Level 1 devices. In this command, Level 1 is specified. The second command is coast style, which is used to configure a coast type. The most common coast types are narrow and wide. The wide type supports more extensions, such as the is extension for TE. Therefore, to support SRv6 TE policies in the future, we can configure the wide type. Then, we need to configure a network entity title. After that, we can enable IPv6 for the IPv6 topology by running the IPv6 enable topology command. This command has two key parameters, standard and IPv6. In standard mode, IPv6 and IPv4 can share the same topology. As such, IPv6 can also use topology 0 of IPv4 to calculate routes. In this case, however, if some devices on the network are not configured with IPv6 addresses, the devices cannot perform IPv6 forwarding. Therefore, you are advised to specify the IPv6 parameter to ensure proper forwarding in an SRv6 scenario. In this way, IPv6 calculates routes based on its own topology, avoiding forwarding black holes. Now, let's look at interface-specific is configuration. Is is a link-based protocol similar to OSPF v3. However, it's different from OSPF. This is because OSPF is a subnet-based protocol that requires the network command to be used to enable a specific subnet. As is based on links between interfaces, it needs to be enabled on the specified interfaces. Before enabling is on an interface, we should enable IPv6 and configure an IPv6 address for the interface. In most cases, is needs to be enabled on all the involved physical interfaces. You are also advised to enable is on loopback interfaces of P1 and P2 so that the two PEs can communicate through a loopback route. This operation facilitates the subsequent establishment of a BGP EVPN peer relationship between P1 and P2. After the preceding configurations are completed on P1, the P, and P2, is-neighbor relationships can be established using is-hello messages. Is supports broadcast networks and P2P networks, and the formats of hello messages on these two types of networks differ slightly. Let's take is-neighbor relationship establishment between P1 and the P as an example. First, P1 sends a hello message to the P. In this message, the sysid field is set to P1 and the NBR field is none. After receiving the hello message, the P finds that the value of the NBR field is not its local MAC address. The P then initializes its neighbor P1 and returns a hello message to P1. The values of the sysid and NBR fields are now P and P1, respectively. We can see that this value is P1's MAC address. After receiving the hello message, P1 sets the state of its neighbor P to up, and then sends another hello message to the P, with the sysid and NBR fields set to P1 and P, respectively. We can see that this value is the P's MAC address. After receiving the hello message, the P also sets the state of its neighbor P1 to up. In this way, an is-neighbor relationship is successfully established between P1 and the P. The process of establishing such a neighbor relationship between P2 and the P is similar to this. Now let's look at the common is-hello message format by using this hello message as an example. It carries several common TLVs, such as the area address, protocol supported, and is-neighbor TLVs. Note that the neighbor MAC address is carried using the is-neighbor's TLV. Another one is the IPv6 interface address TLV. This TLV carries link local addresses, which is can use to establish neighbor relationships. Below the IPv6 global interface address TLV, we can see the multi-topology TLV. This TLV indicates that the IPv6 topology is supported. In this example, topology 2 and topology 0 are used for IPv6 and IPv4 respectively, matching the earlier configurations. After the neighbor relationships are established, The devices exchange is link state PDUs, referred to as LSPs, to achieve LSDB synchronization. This figure shows the process of exchanging is LSPs between the devices. Is LSPs contain two types of key information: interface address information and subnet information. Here, we can see a series of interface addresses and their corresponding subnets and prefix lengths. After an LSDB is generated, ISIS uses the SPF algorithm to calculate routes. The involved routing information consists of interface addresses and subnet route information. To check ISIS routing information on P1, we can run the display ISIS route command. Here, we can see that the routing information displayed in the command output is consistent with that carried in corresponding ISIS LSPs. Note that the next hop addresses in the ISIS routing information are link local addresses, not user-configured global unicast addresses. ISIS needs to maintain LSDB synchronization, which is usually achieved through CSNPs and PSNPs, ensuring that all the involved devices have the same LSDB. In addition, all the devices can obtain the same routing table by running the same algorithm. Now that we are familiar with ISIS configurations, let's look at SRv6 configurations. For SRv6 configurations, we should enable SRv6 globally and then configure a source address for SRv6 encapsulation. This example uses the loopback address on P1 as the source address. This is also the recommended configuration. After that, we need to configure a locator, which is an IP address prefix. Here, 64 indicates the prefix length, and 32 indicates the length of the segment that can be allocated to static seeds under the locator. In this way, we can use the locator to represent P1. In most cases, you are advised to ensure that each locator is unique in the SRv6 domain. But, in some multi-source protection scenarios, different devices may be configured with the same locator. That's all about basic SRv6 configurations. After the configurations are completed, ISIS needs to be used to send SRv6 information. This can be achieved using the segment routing IPv6 locator command. This command has three functions: enabling ISIS SRv6, advertising the corresponding locator route, and enabling ISIS to dynamically allocate seeds if static SRv6 AND or AND.x seeds are not configured. In SRv6 BE scenarios, AND and AND.x seeds are generally not used. Therefore, we can specify the auto seed disable parameter in the command to disable ISIS from dynamically allocating seeds so that ISIS can only advertise locator routes. This helps conserve device resources. Generally, SRv6 does not need to be configured on a P. After SRv6 configurations are completed, a local seed table is generated based on locally configured seeds. The seeds can be dynamically allocated by ISIS or manually configured. Next, let's look at a common local seed table. We can see that this table contains two AND seeds and two AND.x seeds. All of these seeds are dynamically allocated by ISIS. If we look at the detailed information about the AND.x seeds, we can see that each of them is bound to an outbound interface. Moving on, let's look at the format of ISIS LSPs carrying SRv6 information. These LSPs carry a lot of SRv6 related information in comparison with common ISIS LSPs. For example, they carry the router capability TLV, which contains the SRv6 capability sub-TLV, node MSD sub-TLV, and IPv6 TE router ID sub-TLV. The node MSD sub-TLV is used to advertise the maximum SRh stack depths that can be processed by a node. The LSPs also carry the SRv6 locator TLV. In addition to advertising locator and prefix length information, this TLV is also used to advertise associated AND seeds. In this example, the seeds are dynamically allocated by is. Some of the seeds carry the PSP flavor, but the others do not. PSP means penultimate segment pop of the SRh, and it is similar to the PHP flavor in VPLS forwarding. Next, let's look at the multi-topology is reachability TLV carrying AND.X seeds. Similarly, some of the AND.X seeds carry the PSP flavor, but the others do not. In addition to the TLVs mentioned earlier, the LSPs also carry an IPv6 interface address TLV and a multi-topology reachable IPv6 prefixes TLV. In comparison with the TLVs used in common is LSPs, the multi-topology reachable IPv6 prefixes TLV carries a type of key information, locator root. This root is similar to an SRv6 locator root, which is a clever design in SRv6. Because only SRv6 capable devices can identify the SRv6 locator TLV, but common is devices cannot. The multi-topology reachable IPv6 prefixes TLV needs to be used to advertise locator root information so that SRv6 capable devices and common IPv6 devices can coexist on a network. In this case, SRv6 incapable devices can use this TLV to obtain SRv6 root information. Huawei devices use this TLV to obtain locator root information regardless of whether SRv6 is supported. Because this TLV does not carry algorithm information, Huawei devices use the SRv6 locator TLV to obtain locator root information in flex algo scenarios. After updating SRv6 information, is updates the LSDB and then uses the SPF algorithm to calculate roots. Let's take the is routing table on P1 as an example. We can see that two new root records exist in the routing table. One indicating the locator root of P1 and the other indicating that of P2. Now let's look at the is routing table on the P. The table shows that SRv6 roots are generated even though SRv6 is not configured on the P. This explains why SRv6 capable devices can be deployed together with common IPv6 devices. After completing SRv6 configurations, we need to configure BGP. The first step involves configuring CE access on the PEs. Specifically, we need to create a VPN instance on each PE, bind a specified interface to the VPN instance, and then configure an IP address for the interface. The next step involves configuring routing information exchanges between each PE and its connected CE. The exchanges can be implemented using multiple types of routing protocols, such as eBGP, iBGP, IGP, and static routing protocols. Here, we'll use BGP as an example. During BGP configuration, we need to enable the peer relationship in the corresponding VPN instance address family on each PE, and in the corresponding public network instance address family on each CE. Using the network command, we can enable a CE to advertise its subnet routes to a PE. When configuring BGP on a PE, we can specify a router ID. Because an SRv6 public network is usually an IPv6 network, if the PE is configured to automatically generate a router ID, this router ID may conflict with another PE's router ID. If this is the case, a BGP EVPN peer relationship fails to be established between the PEs. For this reason, we can manually configure a router ID to ensure that the BGP router IDs of devices do not conflict with each other. After that, we can run the opcode AND-DT4 command to configure an AND.DT4 seed for the specified VPN instance. This operation is optional. You can also use an AND.DT4 seed dynamically allocated by BGP. An AND.DT4 seed consists of two parts, that is, locator and opcode, which together form a seed in the IPv6 address format. Although the seed appears to be the same as a common IPv6 address, it contains a lot of information and functions as an instruction. The locator part in an AND.DT4 seed directs packets to a specific PE in the SRv6 domain, and the opcode part helps the PE identify a specific VPN instance. To achieve these two functions in a conventional BGP MPLS IP VPN scenario, two labels need to be used. Specifically, an outer MPLS label needs to be used to direct packets to a specific PE, and then an inner VPN label needs to be used to help the PE identify a specific VPN instance. In an SRv6 scenario, however, this can be done by using only an AND.DT4 seed. Now let's look at the AND.DT4 seed generated on a PE. This type of seed has only local significance. In this local seed table, we can see that the AND.DT4 seed is bound to a specific VPN instance. Next, we need to establish a BGP EVPN peer relationship between the PEs to transmit the routing information of the CEs. This involves specifying an IPv6 peer and configuring a loopback interface for peer relationship establishment. Note that using loopback interfaces in this case improves the robustness of the BGP peer relationships. Following that, we need to enable the peer in the L2 VPN EVPN address family. In this way, the BGP EVPN peer relationship is successfully established. The configuration involves several key commands, the first of which is used to enable a VPN instance to advertise routes. After this command is run, the routes of the specified VPN are advertised as Type 5 EVPN IP prefix routes to the peer PEs through the BGP EVPN peer relationship. The second command is used to add seeds to the BGP EVPN routes to be advertised. The third command is used to enable EVPN L3 VPN in SRv6 mode. EVPN supports several modes, such as the VXLine mode, but we'll use the SRv6 mode in this example. After EVPN L3 VPN in SRv6 mode is enabled, EVPN route recursion is performed based on the seeds carried by the EVPN routes. If no static AND.DT4 seed is configured for the specified VPN instance, BGP dynamically allocates an AND.DT4 seed after the command is run. The last command is used to configure a device to advertise EVPN routes carrying SRv6 encapsulation attributes to its peer. After the configurations mentioned earlier are completed, the devices exchange open messages to establish a BGP peer relationship and use keep alive messages to maintain it. Once the peer relationship is established, the devices exchange update messages carrying path attributes and EVPN and ALRI. Now let's look at the formats of BGP open and keep alive messages. An open message carries L2 VPN EVPN address family capabilities and other capabilities. L2 VPN indicates the main address family type, and EVPN indicates the sub-address family type. Some of you may wonder why an L2 VPN mean address family instead of an L3 VPN mean address family is used here. This is because EVPN was initially developed to reduce L2 VPN control plane complexity and subsequently extended to support L3 VPN. Originally, in scenarios where EVPN lacked support for L3 VPN, a network deployed with both L2 VPN and L3 VPN required not only L2 VPN peer relationships, but also VPN v4 or VPN v6 peer relationships to be established. This gave rise to a large number of BGP peer relationships. Because EVPN has now been extended to support L3 VPN, only one EVPN peer relationship is required to complete the tasks of the preceding address families involved. This greatly simplifies protocols. As for a BGP keep alive message, it contains only a BGP header. Next, let's look at the BGP update message format. A BGP update message carries multiple types of path attributes. In this example, we can see that the message also carries the extended communities attributes with an EVPN root target, which is also called an VPN target. We can also see the SRv6 related BGP prefix seed attribute, which carries an end.dt4 seed. Below it, there is the MP-rich NLRI attribute carrying EVPN network layer reachability information, referred to as NLRI. In this attribute, we can see that the involved address family is an L2 VPN EVPN address family. The involved root is a Type 5 EVPN IP prefix root, and the root carries RD information. The prefix and prefix length of the root are also displayed. A BGP EVPN routing table is generated based on received BGP update messages. Let's take PE1 as an example. We can see that the BGP EVPN routing table on PE1 already contains the root of CE2. For the expression format of this root, the first digit 0 is the fixed value of a Type 5 IP prefix root. The middle address indicates a host address, and 32 indicates the mask length. The next hop of the root is a loopback interface address belonging to PE2. According to the details about the Type 5 IP prefix root, the root carries RT and RD information. Most importantly, the root carries a prefix seed, which is also the end.dt4 seed of the root, and the root type is Type 5. Now, let's verify the preceding configurations and see how a preferred BGP root enters an IP routing table. The root first enters the routing table of the corresponding VPN instance. Let's take this highlighted root of CE2 as an example. Note that the next hop of the root has been changed to the end.dt4 seed on PE2, and the outbound interface is displayed as SRv6 BE. This indicates that the root has successfully recursed to an SRv6 BE path. In addition, the flags field of the root is displayed as RD, indicating that the root is a recursive one. PE1 needs to send this root to CE1 through the BGP peer relationship between them. After the root is received, it first enters the BGP routing table of CE1, as shown in the command output. The preferred BGP root on CE1 then enters the IP routing table. We can see that this highlighted root is learned through an eBGP peer relationship. After we run the ping command on CE1 to ping the IP address of CE2, the ping operation succeeds. This indicates that the configuration is successful. After introducing the control plane implementation of EVPN L3 VPN v4 over SRv6 BE, let's see how packets are encapsulated during forwarding. In this example, a ping operation is initiated from C1 to C2 to simulate packet encapsulation. First, C1 indicates a ping packet, which is an ICMP request packet. C1 performs IPv4 encapsulation for the packet, setting the source address to C1's address and the destination address to C2's address. After receiving the packet from C1, P1 performs SRv6 encapsulation, setting the source address to that previously configured for SRv6 encapsulation, and the destination address to the next hop of the corresponding IPv4 route, that is, the end.dd4 seed carried by the route. We can see that the SRv6 encapsulation does not involve any SRh. The packet shown on the right is an ICMP reply packet sent from C2 to C1. It is a ping reply packet and corresponds to the ICMP request packet. In response to the ICMP request packet, C2 generates an ICMP reply packet and performs common IPv4 encapsulation for it. After receiving the packet from C2, P2 performs SRv6 encapsulation. For this packet, the encapsulated source address is the SRv6 source address configured on P2, and the destination address is the end.dd4 seed carried by the corresponding route. That's all about the encapsulation of packets in an EVPN L3 VPN v4 over SRv6 BE scenario. To conclude this course, let's summarize what we have learned. We first talked about route advertisement, which consists of 5 steps. The first step is to advertise the routes of C1 to P1 through a peer relationship. Although we used an eBGP peer relationship, we could have also used an iBGP or IGP peer relationship. Before the advertisement, the preferred routes in the IP routing table can be imported to the BGP routing table. The BGP routes on C1 are then advertised and imported to the routing table of the specified VPN instance on P1. The second step is to run the advertise L2 VPN EVPN command on P1 to enable the specified VPN instance to advertise EVPN IP prefix routes. The routes then enter the EVPN routing table. The third step is to advertise Type 5 EVPN IP prefix routes through the BGP EVPN peer relationship between P1 and P2. The fourth step is automatic EVPN route import to the VPN instance-specific routing table based on carried RT information. The last step is to advertise routes from the VPN instance-specific routing table on P2 to the BGP routing table on C2 through an eBGP peer relationship. In addition, the preferred routes in the BGP routing table can be added to the IP routing table for forwarding. Now, let's look at the data forwarding process. Assume that C1 sends a packet. Common IPv4 encapsulation is performed for the original packet content. After receiving the packet from the interface bound to the specified VPN instance, P1 searches the routing table of the VPN instance according to the destination address in the packet, finds the associated SRv6 VPN seed and next hop information, and then performs SRv6 encapsulation. After receiving the packet, the P also searches the routing table according to the destination address in the packet. Because SRv6 is not configured for the P does not have any local seed table. Consequently, the P forwards the packet to P2 through the specified locator route. P2 searches the local seed table according to the outer destination address and finds a matching end.dd4 seed. Then, PE2 performs operations as instructed by the seed. Specifically, PE2 decapsulates the packet, removes the IPv6 header, searches the routing table of the corresponding VPN instance according to the inner destination address, and forwards the packet to CE2. That's all for this course on EVPN L3 VPN v4 over SRv6 BE. Thank you for watching.